I'm Sue Nelson and welcome to the Planet Earth podcast. This week we're in Oxford to meet the man who not only had a hot date with an active volcano, but has witnessed the Earth splitting apart. I can accurately predict that there's some space weather ahead and news of what's been described as mechanical dolphins on their way to Antarctica.
They move up and down in the upper kilometre of the ocean, making measurements of the temperature of the water and how salty it is. And every time they come to the surface, they phone home.
It may seem relatively peaceful, but the Earth is under constant bombardment from the Sun. Our nearest star spews out a stream of charged particles at speeds of around 1 million miles an hour. We're protected from this stream by a magnetic bubble called the magnetosphere, but sometimes that isn't enough. A large solar eruption can do serious damage, knocking out satellites or disrupting power supplies. After a period of calm, the Sun's activity is expected to increase over the next few years, so it's important to be able to predict when solar storms are heading our way. Richard Hollingham went to meet geomagnetist Alan Thompson in the basement of the British Geological Survey in Edinburgh to uncover the history of space weather forecasting.
Behind this door is our new archive store, and we've brought all our magnetic records from the various magnetic observatories in the UK, and we've brought them here to Edinburgh to keep them in a safe, secure environment, to protect them for posterity, and also to get more science out of the information that's in them.
And when you say a magnetic record, that's a record of the Earth's magnetic field, of fluctuations in the Earth's magnetic field?
That's right. Our instruments record small, really small changes in the Earth's magnetic field, maybe on a normal day, maybe a few tenths of a degree in the compass direction. And we're doing that 24 hours a day, 7 days a week, all the time, and we have been doing it in the UK for getting on for 160 years.
Now, we're here to look at a particular year, 1859, so let's go and have a look.
Let's go.
An appropriately creaky door. Let's shut that behind us. So down a ramp and into the archive, as you'd expect. Stacks of cardboard boxes with various things. Q 1909 to 1910, that one says. These are all labelled as well. 1876, 1850. Here we go. Well, look at what we're after. 1859. So that's over. Oh, here we go. So 1859. So what's this represent? What's in this box?
Okay, this box contains photographic records of the instruments that were running at the Greenwich Magnetic Observatory in 1859. And it was photographic paper, so essentially in those days they had little more than a magnet on a string with a mirror on it reflecting a beam of light onto a piece of photographic paper. So in this box we've got the volumes of all the magnetograms, the daily records for that year, and in there is the event we're looking for.
Okay, so that's...
If we just open this...
It's all wrapped in tissue paper.
Because we want to preserve it.
It almost looks like ancient parchment, doesn't it, with this wiggly line on. This was from photographic paper, and then the marks along it. And this one here, what's this, August 31st,
So
1859.
It runs from August 31st into the 1st of September. And we've got two traces here. One of them is the variation of the compass needle on that day. Now, most of the time it doesn't change too much. It's a few tenths of a degree change on a normal day. But in this event, towards the end of the record, there's a sudden blip.
It's right off the scale.
Yeah, it's huge. It's a few tenths in just a few minutes of activity. And that marks the arrival of X-ray radiation from the Sun. So it's taken 8 minutes from the Sun. Something's happened on the Sun on that day. And we're seeing the first record of that. And the way that works is the X-rays ionise the gas in the atmosphere, and those electrical currents cause magnetic field. And that's what our instruments measure. So we've picked that up, and we know this event followed what was known as a solar flare. The first one was witnessed by eye by the astronomer Richard Carrington. So his claim to fame is that it's now named after him. It's the Carrington event of 1859, and it's the biggest magnetic storm that we think we have in our records.
So in 1859, would anyone have noticed that? If they weren't measuring it, would anyone on Earth have noticed this solar activity?
Yeah, well, this was the Victorian era, and we had a telegraph system. Some people have dubbed it the Victorian internet. The telegraph operators normally would use batteries to power this system, But when the aurora borealis was in full swing, they didn't need to, they just disconnected. And the natural electromagnetic variations from this big solar activity, this magnetic storm, could power the the Victorian internet directly.
So they could power the telegraph directly from the sun?
Yeah, and there's reports of fires and people getting electric shocks as well. So it was not a trivial thing happening at the time.
The point really is that in the early days of electricity, when you had things like the telegraph, this could have an impact. If this happened today, 150 years on, big deal.
It's a big deal, and that's why we want to get to grips with it. So, in a sense, this is a natural hazard to add to other natural hazards.
OK, Alan, we've come to the opposite end of the building. We're up on the roof now, and this is how you do it these days.
Yeah. So nowadays we have a series of automatic instruments that run at remote locations called magnetic observatories, and we have 3 of them in the UK. And the instrument we've got in front of us is one method that we use to calibrate those automatic instruments. And we need to do these observations at least once a week, so we know we've got an absolute measure of the magnetic field.
Now, Chris Turbot, you've set this instrument up for us. What can it measure? It looks almost like a surveyor's tool, levelling a bridge or a road or something.
Yeah, this is exactly what it is. You'll probably see surveyors using these at the side of the road. It's a yellow theodolite sitting on a wooden tripod. It's a little bit different in that all of the magnetic content's been taken out, so there's no iron and steel left in there. It's all been replaced with copper and brass, etc. And it has been adapted because we've put on the top of it, this is a fluxgate magnetometer, and it's a little instrument that's sensitive to the direction of the magnetic field along which it's pointing. And the idea of it is that we can rotate it around, the theodolite gives us the angle, we can rotate it around and search for the direction of the magnetic field. And it'll give us an audio output depending on the size of the magnetic field, and we just rotate that round until we can find the direction of magnetic north. Okay, so that's telling me that we are actually off slightly. If I just rotate it, the theodolite round with the magnetometer on the top of it, it will go through. I just went through it there. I'll just go back a little bit until there we go. Oh. There we go, that's at 0, so that's us lined up. What it's doing, we've probably got the microphone a little bit close to it, so it's actually picking up the effect
so it's picking
of
up the microphone, yeah.
Yeah, exactly, yeah. It's that sensitive. If I can zero it, I've got a paperclip here. If I just move that within a few centimetres of the instrument, you'll hear that it's sensitive.
So it's that sensitive, it can detect a paperclip?
That's right, yeah. We're trying to measure the magnetic field. The magnetic field is about 50,000 nanoteslers. We're trying to measure about 0.1, so that's about 2 parts in a million that we're trying to measure the strength of the magnetic field with. So the instruments have to be very, very sensitive.
Now, what's the point of doing this other than to build up a past record? Can you use it to predict what's going to happen?
Well, one of the things we do is we exchange data with other institutes around the world, and that allows us to build up models and maps of how the field is changing. And in part of that process, yes, to some extent, we can predict the long-term change in the magnetic field, but realistically only up to about a year ahead, which is why it's a continuous process of measuring and modelling to build better maps. And with a bit of scientific insight, yes, we'd like to push that a bit further ahead than just a year ahead.
And do you think in our lifetimes we'll see anything like that 1859 event?
There's every chance of it. It's very hard to quantify how frequently such an event should come round. But the sun is very variable, and it's entirely possible that we can get an event like that, well, maybe every 100 years, but it's hard to tell, and that's one of the reasons why we have to keep looking into the records to try and get a better understanding of just how frequent that might happen.
Alan Thompson from the British Geological Survey in Edinburgh. You're listening to the Planet Earth podcast, this week from the Department of Earth Sciences at Oxford University, where I'm joined by geologist David Ferguson, whose research focuses on volcanic activity in one of the remotest places on Earth. David, I think you better describe where exactly your research is taking place.
So our research is focused on the Afar Depression, which is a great vast desert in northern Ethiopia, which is one of the remotest, as you say, and also one of the hottest places on Earth.
Why the interest in that? Obviously, it sounds interesting just purely by its location,
Yes.
but what, as a geologist, interests you?
Well, Afar geologically is a fascinating place because it's one of the few places on the Earth's surface where we can see the continental crust, and that's the rocky outer shell of the Earth that we live on. We can see it being ripped apart by the movement of tectonic plates, and hot magma from the Earth's mantle, which is the region below the crust, wells up to fill the gap and creates a new ocean basin.
How long have geologists known about this particular region?
So the first geologists to visit Afar were probably there during the 1960s and the 1970s, and it was recognised at this point that it was an exceptional place to understand how plate tectonics work. Unfortunately, due to the independence war between Eritrea and Ethiopia, we haven't really been able to visit the area for decades. So it's only in the last 10 years or so that scientists have been able to get back into Afar and been able to study in detail the processes that are going on there.
Before we go into the processes themselves, you've brought a couple of rocks here. Describe
Yes.
to me and to us what this surface, this area of this rocky, remote place looks like.
So in this bag we have a piece of basaltic lava. This is one of the most common rocks on Earth, actually, and this is one of the newest rocks on Earth. This is just approaching its first birthday. So this piece of their surface was underground a year ago. And
It's almost like a hard, black, grey piece of sponge, very
so it's
porous.
full of holes. So these were all the gas bubbles that escaped. It's quite spiky because it flowed across the surface, and it's still young enough to preserve all these spiky bits. And if you look carefully, you can see it's full of shiny crystals, large white, kind of glassy-looking crystals.
Oh, yes.
And these grew underground in a magma chamber where this lava was stored before it erupted. And it's this other. We have another piece of rock here, which is very different. There's no bubbles in this, and this is a piece of volcanic
Very
glass.
shiny.
It's incredibly shiny.
Almost looks like black marble.
Yep, it's very heavy, and it's composed almost just entirely of glass.
Let me just feel a bit. It's like the size of a bag of sugar,
Yeah.
this bit, and actually feels pretty much probably a bit heavier than a bag of sugar
much
as well.
yes. And the difference between these two really is their chemistry. And this magma was so viscous that the crystals that we see in this lava weren't able to grow, and so it's just solidified into a chunk of glass, really.
Now, this great big rift, you say it's an ocean-forming rift. Does that mean in the foreseeable future that the area, this part of Ethiopia that you're looking at, will be covered in sea in, I don't know, hundreds of thousands of years' time?
Yes, so the crust that forms Ethiopia is being slowly stretched apart at about 20 millimetres a year, for instance. However, right now in Afar, that process within the last 5 years has speeded up dramatically, and it's moved approximately a metre a year within the last, or 2 metres a year even within the last 5 years. We think this probably goes in stops and starts, and so at the average speed of maybe 20 millimetres a year, if this continues for 10 million years, for instance, then we would probably see a new ocean basin in Afar.
How normal is this for a geologist to actually see this taking place?
It's incredible. It's pretty much a once-in-a-lifetime opportunity. Tectonic plates move very slowly, and it's not common that we get a chance to witness a kind of furious stage of activity. One other well-documented phase, which was in Iceland in the 1970s. But apart from that, this is a very rare occurrence. And we think in this part of Afar, it probably happens every 400 to 500 years.
So how often do you get to go out there? Because I know from reading, you kept a blog at one stage last year that you had this hot date with a volcano. So how likely are you to go out there? Or do you go out there as soon as you hear that there's activity? Is it like being like a fireman on call, or the geologist equivalent of a fireman?
Yeah, a little bit. We're volcanologists on call. We go out for two reasons. We go out to collect rock samples from older lava flows to perform experiments on. But yes, as you say, when we hear that there's an eruption, we try and get out there as quick as we can because we want to collect samples and we want to actually witness these eruptions in progress if we can, to learn a little bit about it. We're always ready to drop everything and run out if we get the opportunity.
David Ferguson, thank you very much. And if you're in London between the 25th of June and the 4th of July, do check out the Royal Society's Summer Science Exhibition, because David will be there with the rest of the research group with a stand all about the project called Fast and Furious, witnessing the birth of Africa's new ocean. The world's largest gathering of polar scientists recently took place in Oslo. Around 2,000 scientists took part, and among them was Professor Karen Haywood, a physical oceanographer from the University of East Anglia. She's preparing for an unusual robotic ocean gliders project around the Ross Ice Shelf in Antarctica that's about to officially launch on the 1st of July. I caught up with Karen at the conference in Norway and found out all about it.
These ocean robots are a bit like mechanical dolphins, and they move up and down in the upper kilometre of the ocean, making measurements of the temperature of the water and how salty it is. And every time they come to the surface, they phone home on an Iridium mobile phone, just like you or I do, and give us their data and receive commands for where they're going to go next.
That's amazing. I mean, you say robotic dolphins. Are they the size of a robotic dolphin?
They're not that different to a real dolphin. They're about as big as a person. Bright yellow. Ours are bright yellow. They're very clever. The way they work is they don't have a propeller. They work by pumping oil from one side of a bladder to another side, and that changes the buoyancy of the instruments, so they rise up or go down into the ocean.
And what is actually inside them then? Because you say they can do all these things, and they must be filled with all manner of equipment.
We've got 3 different instruments on ours. Temperature and salinity. They also measure how much oxygen there is in the water, and they measure how much chlorophyll, how much green plants there are, and they measure how much backscatter of light there is, which is essentially how murky the water is.
So they're in this specific area at the moment, or they're about to explore the Ross Sea. And what in particular are they looking for?
It's a multidisciplinary project, and we're looking for the processes that drive the production of plankton, the chlorophyll, the phytoplankton plants. So we're looking at the physical processes from the wind, the interaction of the water with the ice. We're going to be very close to the Ross Ice Shelf, and it's a very interesting area for the interaction of the physics and the chemistry and the biology.
And why do it this way instead of using conventional methods like scientists on the ground who are at the bases there in Antarctica, or using research ships?
Well, there's a number of reasons, and I think sea gliders are going to be the way forward for the next decade. One is that they're cheaper than research ships. Research ships are very expensive. They burn an awful lot of oil, so emit a huge amount of CO2 into the atmosphere. But there are also things that you can do with gliders that you can't do in any other way. And one of them is that you can go there when the weather is really rough, and another is that we're going to be using them in the Ross Sea. There's a fair amount of sea ice, and you can now use these gliders to go under the sea ice. So that's going to get us unique data that we can't get in any other way.
You mentioned that these robotic dolphins, these ocean gliders, can phone home, come to the surface and phone home. So does that mean you've got to wait for it, or could you get your data now off your mobile phone?
I could actually get my data right now off the mobile phone if you'd like to see some.
I think I need proof of this, definitely.
Okay.
Here we
So
go.
I've got my iPhone now. And
There's that characteristic interference on the microphone.
And all I need to do is log into my email, and sure enough, here is an email from the UEA Sea Glider. It's just phoned home with some data. We haven't started the Antarctic work yet, but we do have one glider which is in the water off the west coast of Spain, and this one is calling home once an hour to send us the temperature data, and we're able to put these on our website, and anybody can access them. The data are on the website within a few minutes of us receiving them.
And we hope to bring you more news of that project from Antarctica later in the year. A brief preview now of how to get to the other end of the Earth, as regular Planet Earth presenter Richard Hollingham is preparing to go to the Arctic in an icebreaker ship with the Scottish Association for Marine Science. But first, there's the important matter of sea survival training.
Here we go with the jump off the 4-metre high platform into the water. I have to say it looks a lot higher than 4 metres. Here it goes. Well, apart from managing to punch myself in the nose on the way down, I've got blood dripping down my chin. I seem to have come out relatively unscathed, still alive.
You can hear more of Richard's experiences on our Facebook page. Plus, communications permitting, you'll be able to follow his progress on board the ship on the Planet Earth Online website. Next time, we'll be reporting from the Arctic. I'm Sue Nelson, and this has been the Planet Earth Podcast. Thanks for listening.